So today's lesson, we're going to look at making inferences from sample surveys. Inferences is really just a statistical math word for drawing conclusions, right? So can we draw conclusions from sample surveys? How do we do that? So here are our objectives. First is estimate population parameters using collected data from a sample. The second is to then analyze the estimated population parameters. What can we learn from them? Can we draw some conclusions? And then the third is to find a margin or margins of error for a survey. Right, little vocabulary review here, right? We're going to keep using these terms population and sample. So I just want to reinforce that the population is the collection of all data, such as responses, measurements, or counts that you want information about, right? This would be for every, person in the United States, for example. A sample is a subset of the population, right? So we can't ask everybody in the United States, but we can ask a subset of that. We refer to that as our sample. And then the numerical description of the population characteristic is called our parameter. And the numerical description of a sample characteristic is called a statistic. So generally what we do is we collect data from our sample, we determine the statistic from that sample, and then we ask ourselves, does that statistic fairly represent the parameter, right, of the entire population? All right. So if we're going to estimate the population parameters, there's kind of two ways to approach this, right? There's two main branches of statistics. The first is what we call descriptive statistics. So that involves the organization, summarization, and display of data. Okay, so we'll be collecting data, putting it into a table, maybe calculating the mean or the standard deviation, and then perhaps graphing it. Inferential, big word, inferential statistics involves the using of a sample to draw conclusions about a population. Okay, so sometimes we do both, right? We have to describe the statistics first, but the real value comes from drawing conclusions about the entire population from the statistics that we study from the sample. So that's where we're going to focus today, right? How do we draw those conclusions about the entire population? So here's another way to say it. We can use statistics to make reasonable predictions or inferences, okay? So that's how we're going to think of this word inference, is to make a reasonable prediction about an entire population when the sample is representative of the population. All right, so the first thing we're going to look at is estimating a population mean. So let's look at this example. The number of friends for a random sample of 40 teen users of a social media networking website are shown in the table. And then we're being asked to estimate the population mean, mu, right? So this is the parameter of the population, but we have statistical data, right, to look at and then draw some conclusions. So here's a table. Here's how we've organized the data. We just put all 40 values into this table here. And if we want to find the mean, right, we know how to find the mean. We have to add up all the values of X. That's a little summation symbol there, and divide by the number of samples. Okay. Now, it turns out if we add up all these numbers, we get 11,996. We divide that by 40 and we get 299.15. Now, it would be kind of tedious, right, to sit here with a calculator and add up all 40 of these samples. Right? Could very easily just make a few errors and our answer would be off and we wouldn't even know it. What's a better way to do that? Well, remember earlier in the unit, right, we used a spreadsheet, right, to do the math for us. So we could do the same with this problem, right? We could take these values, enter them into a spreadsheet in the same way that they were presented, or we could just put them all in a single column and then simply use the function average, right, to find the average. So notice in the spreadsheet, we're going to take the average of all the values that are in the range from A2 to E9, right? All 80 values, okay? And we can do that much quicker probably than on our calculator and with far fewer errors. All right, so what can we conclude then about the estimate of the population mean? Well, we can say that the mean number of friends of all teen users is about 299, okay? We've got a fairly large sample size here. Now note, the probability that the population mean is exactly 299.15 is nearly zero, right? Chances are if we did this again with another 40 people, we wouldn't get exactly 299.15, right? We'd get something a little different. We did it with the entire population. It probably wouldn't be 299.15. It might be, but the probability of that is very near to zero. But because we have a large sample size, right, we can say that the sample mean is a good estimate of the population mean, mu. All right, let's look at another example of estimating population. And we're going to use a word here, proportions. You guys know what a proportion is, right? It's a ratio or a fraction. So it says a student newspaper wants to predict the winner of a city's mayoral election, right? They're going to elect the mayor of the city. 2 candidates, Joe and Donald, are running for office. 8 staff members conduct surveys of randomly selected residents. The residents are asked if they will vote for Joe. Okay, so if they vote for Joe or yes, that's counted. Okay, so that's the second column here. So they've summarized, right, the results of their 8 different samples. And then they calculated what we call a proportion, right? The proportion is simply the ratio, right, of the number of votes for Joe versus the entire number of people that were in that sample. So here's another way to describe that. A population proportion, right, is the ratio of members of a population with a particular characteristic. In this case, that characteristic is they're all going to vote yes for Joe. And the ratio to the total members of the population. The sample proportion is the same thing, except it's just with the sample values, right, that we collected. And so where do these percentages come from, right? If we take that last sample size, we simply take 118, the number that voted yes for Joe or said they will, and divide it by the total sample size of 200, and we get 59%. All right, so what are we going to do with this information, right? Here's the first question. Based on the first 2 surveys, will Joe win? Well, the percentages don't look very good for Joe, right? We would just say no. If that's all the information we had, that's probably what our conclusion would be. However, if we look at the results in all the table, would we draw a different conclusion? And I think the answer is yes. Notice as the sample size increases, the percent of votes for Joe approaches 59%. Okay. So I think Joe can be rest assured that he's going to win the election. All right, let's look at another example here. We're going to continue to work on estimating or analyzing estimates of population parameters, right? So if somebody makes a claim, how would we evaluate that claim, right? An estimated population parameter or claim is our hypothesis. Now, one way to analyze a hypothesis, in other words, to determine whether we think it's true or false, is to perform a simulation. So let's look at the example we're going to work through here. A national polling company claims 34% of US adults say mathematics is the most valuable school subject in their lives. I personally believe that, but I'm a math teacher. So you survey a random sample of 50 adults. You want to say, gee, I wonder if that national polling company claim of 34% is true. I'm going to go out and survey my own 50 adults and see if I get close to their 34%. Okay. So what can we say about the accuracy of a claim that the population proportion is 0.34 or 35% if, when you do the survey, right, 15 adults in your survey say that mathematics is the most valuable subject. Okay, so we went out and did our own survey of 50 adults, and it turned out to be 15 of the 50 said, yes, it's the most valuable subject. Now, here's where the simulation comes in. In order for us to determine whether or not that's a reasonable result, right? In other words, it falls within the range of possibilities. The best thing to do would be to run a simulation. We're going to do it 80 times. In other words, what if we were to simulate that we went out and asked 50 adults this question, and we did it 80 times, right? What are the range of values we might expect from randomly selecting 50 adults out of the entire population? So let's look a little bit at the graph here, make sure we know how to interpret this, right? So let's just take the value that we're interested in, right? 0.34, 34% of the adults think math is the most valuable. Well, if we look at our simulation result and we look at that bar, right, it comes up to the value of 8. That means 8 out of the 80 simulations that we ran yielded exactly the result of 0.34% or 34%. Okay, in other words, agreed with the claim from the polling company. Let's look at some other points here, right? The largest was actually 0.32%. We had 11 of our 80 simulations that came out to be 32%. And we even had some values that were way off to the side here, right? So we had 2 of the simulations actually yielded only 18% or 0.18 of the population saying that math is the most valuable subject, okay? So notice we have a distribution here that looks, right, a lot like a normal distribution. Now, it's not perfect. Real data never is, or even simulation data, right, if it's truly random. But since our simulation data plot is fairly bell-shaped and symmetrical, we can assume the distribution is approximately normal, okay? So that'll be helpful as we work a little further through this example to consider this a normal distribution. All right, back to our first question. What can we say about the accuracy of the claim that the population proportion is 34% if 15 out of our 50 said the same? Well, the first thing we want to do, right, is find that proportion. So 15 divided by 50, our sample size, gives us 0.3. Where is that in our simulation? It turns out that 7 of the 80 simulations yielded that same amount. So what can we conclude here? We could say that, yes, it's likely that 15 adults out of 50 would say math is the most valuable if the true number of the entire population is 34%, because 7 out of 80 is a pretty high frequency in which that result occurs. So our conclusion here is that the claim is probably accurate. Can we say 100% that it's accurate? No, but we can say it's more than likely accurate. All right, let's look at the next case. What can we conclude about the accuracy of the claim if 25 of the adults in our survey said math is the most valuable subject? Well, where would that be in our distribution here of the simulation data? Right, 25 divided by 50 is 0.5. We only had 1 of the simulations out of 80 that yielded that result. Okay, so what can we conclude? We can say that it would be highly unlikely that if we just did a random sample of 50 adults, that half of those, right, would say math is the most valuable, only 1 out of 80 in our simulation, if, right, the true number was 34. Okay, so since it's highly unlikely we would get that result, we can draw a conclusion that the claim is probably not accurate, that it's not 34%. All right, one more question to ask here. So let's assume that the true population proportion is 0.34, 34%. We want to estimate the variation among sample proportions using sample sizes of 50, okay, what we've done in the simulation. In other words, if we were to go out and get any random sample of 50, what are the range of values that we would expect to find and still be able to say, yes, the hypothesis is true, 34% of the population think math is of greatest value. So here we're going to put that normal curve back onto our data here, right? And we know when we study normal distributions that 95% of the possible sample proportions will lie within 2 standard deviations of 0.34, right? If we go 2 standard deviations above and 2 standard deviations below the mean, that accounts for 95% probability. Okay, that goes back to that original chart we had developed for normal distributions. So let's take a look. If we were to exclude the 2 least and greatest values, in other words, we have 2 at 0.18, and then we had 1 at 0.5, it looks like another one at 0.52, what do we have left, right? We would have 76 out of the total of 80 simulation polls that we did, which leaves us with 95%. So there's a 95% probability, right, that if we were to do a random poll, we could get values that fall between 0.2 and 0.48. Okay, if they fell within that range, we could say yes, the true population proportion or the claim that it's 0.34% is more than likely true. So how do we describe that variation? We would say it this way: 95% of the time, a sample proportion should lie between 0.2 and 0.48. And if it does, right, we can conclude that the claim that the entire population is 0.34 is more than likely true. All right. So that's the way we can estimate or analyze an estimate of population parameters, right? How do we determine whether the hypothesis or the claim is likely to be true or unlikely to be true? All right, last topic here, finding the margin of error of surveys. A margin of error gives a limit on how much the responses of a sample would differ from responses of the population. So when a random sample of size n is taken from a larger population, the margin of error is approximated by, and we have a formula here, plus or minus 1 over the square root of n. And n is our sample size. Okay, so pretty straightforward. So what are we really talking about when we say margin of error? Let's look at an example. If 40% of the people in a poll favor a new tax law, and the margin of error is plus or minus 4%, okay, we've already done that calculation, then it is likely that between 36 and 40% of the entire population favor a new tax law. Okay, we can't say that it will be exactly 40, but based on our sample size, we could say that more than likely the entire population would say that 36 to 44% of them would favor a new tax law. So where do those numbers, 36 and 44, come from, right? We start with our sample result of 40, and we subtract our margin of error. So 40 minus 4 gives us 36, and we add the margin of error. So 40 plus 4 gives us 44%. All right, let's do one example together here. In a survey of 2,048 people in the US, 55% said that social media is their main source of news. So what is the margin of error for the survey? That's the first thing we want to find. And then second, give an interval that is likely to contain the exact percent of all people who use social media as their main source of news. All right, the first part, we're just going to use the formula, plug it in, right? We're going to put in the 2,048 for our n value and grab a calculator, right? Square root of 2,048 is about 45.25. 2 decimal places is fine. And then if we go ahead and divide 1 by that value, we get 0.022. Now notice I kept the plus or minus in here, okay? Or if we convert that to percentage, right, that would be about plus or minus 2.2%. Okay, so that's our margin of error, 2.2%. Now, what's the interval? Well, we're going to take the 55% that we got in our survey and subtract 2.2%, so we get 52.8, and add 2.2%, so we get 57.2. So how would we describe the interval? We'd say it this way. It is likely that the exact percent of all people in the US who use social media as the main source of news is between 52.8 and 57.2%. Okay, so that's how we use margin of error. And this is very common. If you see a poll on the news, often at the bottom of the screen, they'll say margin of error. It will say plus or minus 2% or 3% or 4%, depending on the sample size. All right, that's it. So we know how to estimate population parameters. We know how to analyze a claim about the population parameters. Is it likely to be true or unlikely to be true? And then we can find a margin of error for a survey based on the sample size. All right, that's it. Take a look at the assignment.